Hi guys, we're back for part 2 or part B of the multiple choice questions that you covered for Unit 3. A lot of the same themes from part A, so this one should be a little more streamlined. The main focus we have here are on questions that you may see on this year's review. So part A, we just want to talk about gravitational forces. So it's got two asteroids. A, B are kind of the 2 points we want to look at here as far as where they will feel the most gravitational net force compared to B, C. D, you kind of throw that one out because it's in the middle, and so we know it can't be greater, it can't be less than. When you see a problem like this, think about the mathematical relationship that you can use, and our universal constant for gravitation, or Newton's law, gravitational law, is where we're going to go with that one. So here you see the radius is in the denominator, and if we're looking for our net force of gravity, as this goes up, this has to go down, and so we have an inverse relationship. And that's why in this case A compared to B, because they have the furthest radius from one another, that's going to be the most popular, the best answer. Gives an explanation down here. In the end, on this year's exam, they could ask you a question like this. Absolutely. It doesn't have to be in outer space. It could be two students sitting next to each other in a desk. And when that happens, you have to be able to explain why. And so I love this paragraph. It's a great way for you guys to think about how would you word this in a clear, coherent paragraph. And so go back and read through this answer if this is one that stumped you. Okay, number 3 and then 4. We have seen this in a lab situation, right? I had to do it online where it's Sir Isaac Newton. He was whipping rocks around his head. There were lots of different variables that you could adjust, and that's what they have here in the data table. This type of problem says, explain if this is consistent with physics or the facts of physics. This is a really good one, and I would say this one is also one that they might try to propose as a problem that you look at because it's got a lot of good key ingredients of good physics. And so all the data are expected. And when we do that, we want to find an equation that really kind of summarizes all 3 pieces of data. So here we have mass, here we have velocity, here we have radius. So if we look back up here, mass, okay, radius, and what was the other one? Oh, your velocity. So that's your speed. Oh, and then we see speed is the constant in, oh yeah, here we go, varied speed. So when we look at all 3 of these, we just want to think about each data table separately. And if we look at this data table separately using that, what did he call it? Factor of change method, if we keep these constants as a 1 and then we make this bigger, what did it do to the force overall? If we leave these constant as a 1 and we make the mass bigger, what did it do to the force overall? And so that's really what it's kind of showing you right here. Do these correlate with each other when you leave everything else constant or consistent? Using these words inversely proportionate and directly proportionate or positively linear, those are really important words. They're good descriptive words that explain physics of the equation that you use. In the webinar we looked at the other day, they talked a lot about using equations that would be easy for you guys to type. So for example, v raised to the 2nd power, that might be an equation that they would give you and then have you explain rather than have you type it yourself. They said they wanted to kind of look at equations that were simple, like this one, for example, where it would just be F equals 1 over R, for example, because that's a lot easier for you to type in or write than do that. So that's just another little clue from the webinar the other day that might kind of help you identify some equations that they would rather have you derive from F equals ma, nothing's raised to the squared power. So that, again, is one that I see them using as a derivative rather than have you explain. So this one would be more like an explain one. All right, number 5. I've got that one circled because this one was a lot like that free response question that you saw. 3 different planets, different radius, different mass. So what's your best reasoning to support this claim? Again, I really feel like you're going to see those words on this year's exam. So when we go through and we look at these reasonings, you really have to be able to relate it to math. And in this case, the math they're wanting you to look back at again, right here, is that universal gravitation constant equation. And so when we look at varying these variables, and here you see they did a really good job of just doing your factor of change thing here and then simplifying it and combining them, then that's really where they're coming up with this overall effect. Then they sum the equations. So 9 minus 4 is how they arrive at that 5. So again, looking back up here, we see the 4 here. The 4 and the 9 for the mass. We see the 2 for the radius. They're just using these as their multipliers in the equation. So I'm going to put that back up there one more time. I thought this was another one that you might end up seeing something like this on the exam from this section. Okay, number 6 is the next one. Aha, the star and the planet and the center of stinking mass. So here we see that one kind of coming back to haunt us. Center of mass is not going to go away. It's almost every physics concept that we look at, you could ask a center of mass question. So overall, you guys did a great job. You all kind of came up with A, but then it's that second correct answer that you struggled on. And so I just wanted to point this out again, and this is kind of a repeat from last Unit 2's review. Go back and check that out. So again, we think of the planet and the star as a system. And so if we're just thinking about those 2 objects, their center of mass is not technically going to accelerate or change because there's no net force on the system. They have forces on each other, so when they accelerate together, it's going to stay constant. Kind of like 2 students sitting in a desk next to each other. The Earth is rotating around the sun. There's gravitational acceleration, but those 2 objects in a system are going to be moving at a constant rate with one another. And that would be another way to kind of visualize or think about this. And Newton's 3rd law, love that, Newton's 3rd law coming back to haunt us again in this unit. Okay, number 9. Go back again with this one and look at April 10th. This one was a good one for that. Now we're just thinking about graphing it. And here we're showing that centripetal force should have a linear relationship with the distance of the block. Well, what equation helps us to identify that? And if we go back and think about that tangential speed, the tangential speed, again, is constant, so that has to stay the same. And then the radius is in the denominator, and as that gets further and further out, obviously we know tangential speed is going to be related to the distance. So I think when you guys read through this one, remember this whole disk, this part right here, that velocity is not going to change. But if we move this in or out, the speed is going to change when we're closer compared to when we're further out because the distance traveled over a period of time is also going to adjust. So it kind of throws us off when they say it's got a consistent tangential speed. Well, yeah, that's at the edge of the disk. It's going to have a constant speed. But as we move our radius, it also has to adjust. So really, in the end, this is the best answer. Okay, number 9, 11. Yep. Okay, this is kind of a similar question Again, putting a ball at the end of the string, swinging it around your head. And what are we going to see as tangential speed changes when we change the length of the string? Go back to that virtual lab that we did, and I can put that back at the top of the stream for you guys to look at, where Sir Isaac Newton's whipping stuff around his head, because this is a perfect example of it. So here's that equation again, and what happens when we adjust this r, how is that going to change? And then remember, your velocity is also going to be adjusted, but it's squared, so that's why we get half the original speed, because you have to take this, which is squared, over the doubled, and that's where you just get the 2. Okay, 14. Oof. See it again. Here we go. This one, same kind of problem, but how do we measure this? What are the things we're going to need to use in the lab? Again, 2, and pick your simplest 2 that would connect to this equation. So now I feel like we've seen this equation like 7 times in this review. This is an important one that you guys need to go back and review and look at, because perhaps you're just not understanding it, or the question is worded tricky, so it made you not think about this equation. But I would definitely kind of go back and review this one again. For your meter stick and your stopwatch, those are the 2 pieces of information that we're going to answer. The meter stick is for the radius. Meter stick technically could be used to figure out your velocity, but really in the case of a circle, we don't need to think about it because we have revolutions per what? Seconds or minutes. So that stopwatch is really important. And then just the meter stick. So here you see they use time, and then your radius would help you up here in the numerator as well. Okay, next one. And these last 2 I'm going to kind of answer together, number 19 and number 22. I feel like you guys are kind of having trouble with tangential acceleration versus tangential speed. So this first one, it asks you to graph your tangential acceleration versus your, and then in the next one, we talked about tangential speed. So I drew this little picture here. Let's see if I've got it. Oh, I flipped it around. Just to kind of give you guys an idea of what it's describing here. So B and C, I think, were the 2 that maybe tripped us up. Most of you guys picked B. In this picture B, you'll notice my vector arrows for the tangential speed. They're all the same size. And so if they're all the same size, we have a constant centripetal acceleration, meaning that it's not getting faster and faster, it's just staying at a constant speed in that circle, okay? It's constantly moving. For the next one, here you'll see that my force arrows are getting bigger and bigger as we move around clockwise, here starting at about 3 o'clock. They're getting bigger and bigger and bigger. So that means that as I whip this around, it's going to get faster. Trying to do faster here. And so we see an acceleration in centripetal acceleration. Another way to view this is, remember, if something's accelerating, I showed you guys this a couple times this year, get this little smiley face. We're happy when we're going faster. So if your tangential speed is getting faster and faster and faster, we should also have acceleration here, and that's the shape of an accelerating graph. So again, wording might be a little weird, but go back and review graphing and that kind of stuff. And then number 22, here we go. When we think about what equation to pick, keep in mind they said that all of these runners have the same constant tangential speed. So again, that's going to look like this one right here, right? Same constant tangential speed. It does not have a constant acceleration. So that's why this first one doesn't work. All right, see you guys. Check out the last video from Flippin' Physics. Kind of helps you understand number 22. See you later. Bye.